As Mark has already introduced, I'm Srishti. I'm a software engineer at AWS, and I've spent the last few years building some large-scale data and ML infrastructure. And I'm currently based out of the Bay Area in California. Today's talk is titled The Rise of Self-Aware Lakehouses and is a very important topic in today's time. Every modern business in some way has become a data business. And as data grows, it's becoming harder to actually understand what's happening inside our own systems. So in today's session, I'll be talking about how we can make our data platforms smarter and more self-aware systems that can actually understand, optimize, and even reason about their own data. So let's get started. So the agenda for today's talk is going to be introducing some of the modern data architectures like data lake, warehouses, and finally the lake house, the scale of data in today's time, some essential data patterns and characteristics, how to use metadata to make things efficient, and then we'll jump into the demo with respect to the metadata assistant, and then finally some post-analysis. So let's get started. So before we really get into things, what exactly is a data lakehouse, and how do you kind of connect it to what we've had? We've had a data lake, which is where you can store all kinds of data, structured, unstructured. It's flexible and cheap, but it's usually messy and gets hard to manage. So we can think about cloud object stores here. A data warehouse is on the opposite end of the spectrum. It's clean, it's structured, and optimized for fast queries, but it gets limited in scale and flexibility that it offers. And a data lakehouse kind of brings the best of both the worlds together, the scale of a lake and the reliability of a warehouse all in one system. So you'll see this model in platforms like, offerings by some of the companies, like AWS offers SageMaker Lakehouse, Databricks has Databricks Delta, and in many other places, enterprises have adopted this pattern. So what really does this whole lakehouse architecture look like? So it broadly has 5 layers, as I like to classify them. So on the left, you've got data coming in from all kinds of sources. So structured, semi-structured, unstructured, through both batch jobs, streaming pipelines, or there can be other ways in which data is being ingested into your system. And all of this data now lands into the storage layer. So which is basically your cloud object store, where data sits in open formats like Parquet, ORC, Avro. And on top of that sits the metadata layer, as you can see in the diagram here, which is really the brain of the lakehouse. So it can keep track of your schema, versions, transactions, and governance. And frameworks like Apache Iceberg, Delta Lake, Hoodie, they power this layer. And this is also the part that we'll be focusing on today. And above that are the access layers. So the APIs that actually let you query and use this data through SQL, data frames, business intelligence dashboards, and also for your analytics and ML AI workloads. So the key idea here through a lakehouse is simple. Like, instead of maintaining separate systems for raw and curated data, the lakehouse brings it all together into one unified, consistent source of truth. So now that we've quickly gone over the different layers of the lakehouse architecture, let's zoom in on the most critical layer, which is the metadata layer. As I mentioned, this is the brain of the lakehouse. It can keep track of schema, partitions, snapshots, and file versions. And it's also what bridges the gap between a data lake and a warehouse. And this is where we're going to be focusing on today. We are going to understand how we can use, in today's time, how we can use natural language and LLMs to interact with the metadata and extract deep insights instead of writing complex SQL queries. But before we get into, why we're doing this, let's really take a little step back and understand why this even matters. The amount of data we generate has exploded. I'm sure many of you might have heard this common saying that over 90% of the world's data was created in just the last 2 years. And it's so true. like with AI models, maybe even Internet of Things, logs being continuously generated and data from different sources. We're adding hundreds of zettabytes of new data every year. So I don't think we're in the terabyte, exabyte, petabyte zone anymore. We're inching very closely into the zettabyte zone. So this kind of growth in data, it makes it impossible for humans or static dashboards to kind of keep up. We need smarter ways, automated ways to understand what's inside our data lakes and how can we actually make sense of it. So to kind of give you a sense of the scale that I just started talking about, these are just one set of publicly available numbers from a company like Salesforce. For one of their use cases, they are managing over 4 million iceberg tables, holding 50 petabytes of data, and have seen about 1,000x growth in just a decade. And they're not alone. And just imagine querying or governing data at this scale. It's a massive challenge, and it's not unique to just one company. Every enterprise faces some version of the same problem. And there's millions of such solutions that each company or each enterprise will deploy. So all of these add up. So we're just dealing with a lot of data, and we really want to make sense of this data for our workloads. So it's just a lot of companies dealing with the same problem. Even mid-sized enterprises today, they manage tens of terabytes of lake data. Fortune 1000 companies typically are handling hundreds of terabytes to petabytes, and hyperscalers are, I think, easily crossing like exabyte level scale. So the challenge really isn't that we need data, or it's or we have data. So it's really like, how do we really make sense of this data? How do we derive insights from this data and make it meaningful, and ultimately use the insights from it for our production workloads? So that's exactly what brings us to the core of my talk today, which is using metadata intelligently to help teams understand, optimize, and trust their data at this scale. So as we just said, that storing data is not the complicated part. It's managing it, deriving insights from it. There are several challenges which arise, which are the reason why we really need to understand what's happening in our data. What are the kind of things that we need to understand from our data? So the real challenge here is visibility. Most teams or most organizations might not even know what data they have, where it lives, or how it's being used. And this lack of visibility has a great impact on performance. Queries can slow down, costs can go up, and data systems become harder and harder to manage. And when you have say millions of files that are sitting in your data lake, imagine the cost associated with querying them. The IO is going to be so high, and it's going to be so expensive to query these. And the result of all of this, manual work that needs to be done, endless firefighting and manual fixes instead of actually deriving insights or for business value. So I'm sure some of us have gone through this experience where we're just firefighting, trying to figure out, make some sense of our data through some queries. So, and that's exactly where this kind of intelligence, data intelligence, comes in. So using automation and AI, which is the most relevant thing in today's time, to truly help us understand our data and not just store it. So before we, get into intelligence, like data intelligence, let's really pause here and try to understand, what does it really mean to say that you understand your data? What does it mean for you to have a control and understand what's kind of happening in your data systems? So firstly, there's three main things that we could probably classify this in. First, there's structure. So the columns, schemas, and this is the columns, the schema, the partitioning, the relationship across your tables, what kind of partitions exist. Sometimes there can be too many too much data in a single partition, so maybe that cannot be good. That can also result in things like hot partitions and stuff like that. Then there's write patterns, like, are we writing in small files or large files? Is it streaming or batch, or is it some other use case through which we are writing to our data lake? And how often are we writing? Because in streaming use cases, we could be writing like every second or even more frequently. So there's a lot of data that's getting accumulated. So it's really important to understand what do the write patterns look like. And finally, it's also the optimization opportunities. So now that you understand the structure, you understand how you're writing, it's also important to understand how you can actually optimize it, because at the end of the day, you want to be able to derive insights from your data faster. You should be able to clean your data if needed, and so that it can actually be used for the application layer, with respect to maybe some AI ML workloads, for some analytics workload, or any other kind of dashboarding to derive insights from your data or populate the data. So you really need to understand, based on the structure and your patterns, how and what you can optimize in your table. So maybe just simple things like compaction. So compaction is a popular Iceberg table maintenance operation, which will basically just take small files and just combine them into smaller, larger files. So it's just like, think about it as filling a bucket up to a certain size. So that way you have you have lesser, larger files that you're querying instead of all these tiny million files. So you want to be able to understand these kind of optimization opportunities on your table and the data associated with your data lake. And here's the best part, coming back, all of this information already exists in the metadata layer. So in some of the open table formats that I had mentioned earlier, Iceberg, Delta, and Hoodie, so the metadata doesn't just track files, it captures the full context of your data, schema, snapshot, partitions, and even lineage. So it's really quietly the layer that actually powers governance, reliability, and performance across the entire lakehouse. And if you were to ask me, I think that this metadata is an absolute goldmine. It's not just the technical details, it's intelligence that's really waiting to be unlocked. It knows your schema, your column stats, your partition, your file layouts, write frequency, and even the lineage between tables. So and hidden inside this really long metadata file is performance signals, small files, skewed partitions, stale snapshots, and it can really just start pointing you to what kind of optimization is needed and where it can be done. So the question really becomes, how do we tap into all this richness without writing hundreds of SQL queries that can be quite cumbersome and can take a lot of time to figure out, what to really do or how to get these insights? So yes, let's really get into the crux of it, the tool that I built. This is the metadata AI assistant tool that I built. It's self-aware in the sense that it understands the metadata that defines your data lakehouse. So you can really experience the shift from manual querying to instant intelligent insights. So let's play this demo. So yeah, as you can see, we have this little UI here, which is a metadata assistant. I can ask questions to this assistant about the data in my data lake. For the simplicity of this demo, we have a very simple data set where we have about 3 tables in our data lake. So let's see how we can actually ask our metadata assistant some questions and kind of get some insights. So yeah, here, I'm asking it, what are the different tables in my data lake? So here we go. So here we can see that it's telling me that there are 3 tables in my data lake. So I have a customers table. It's telling me the schema, what are the columns like, how many columns are present, what's the data quality stored, what's the size, is there any partitioning, when was it last updated, what are the key columns. So it gives me this high-level summary of all the tables. I have an orders table, a line table. These are partitioned based on dates. There's also some data quality score. It'll also tell me some actionable recommendations that I could probably do for my tables. Like it'll tell me that, okay, one of these tables, the data quality score isn't great. So maybe there's something to, look into here. And obviously this is multi-turn, so you can keep asking questions further. So after we learn about this, maybe, there's another question that I want to ask my metadata assistant. So I'm going to ask it about, what's the schema of my customer table like? So it gave me a high level information, but here it will now tell me, what are the key columns, what are the additional columns, and, it'll go into further details about what kind of things you can do, investigate table growth, look into how, what are the additional details with your table. So, and obviously, all of this is customizable. You can tune your system prompt to to give you the kind of answers that you want to see in your workloads. So it'll give me the reasoning, it'll tell me again about the data quality and things like that. Now maybe I want to learn something else about my so here I'm just going to ask about, are any tables partitioned? Even though it told me before, but maybe in some use cases it might not be. So here it tells me that my line items table and orders table is partitioned by date. The other tables are not partitioned. It'll also tell me to evaluate and see how data is growing in my lake, like how the data is adding up. And then maybe it'll also say like, okay, maybe you could do partitioning for one of the tables because it'll limit the number of queries that the files that need to be opened. So it's pretty neat in my opinion. And then, now maybe I can also ask about performance. Can you rank my tables by query latency or scan cost? So here it will go and tell me that, okay, these are the kind of queries you have. In some of them, you have a lot of files. As the scale is going to increase, it's going to probably become harder. And I think somewhere I had also seen in this response that it does recommend that one of these tables has a lot of small files. So maybe doing compaction might be a way to optimize the performance. So yeah, I guess and there's limit, there's no end to the kind of questions that you can ask this assistant to get insights on your data. So you can ask questions about the structure. You can ask questions about how the data patterns are, what kind of optimizations would they suggest, what's the cost associated, is there any stale data, maybe some sort of, if there's a lot of stale data, then there's also some kind of table operations like Iceberg, like snapshot expiration. So those kind of operations is also what it can suggest. So yeah, that's kind of the demo. So yeah, let's just quickly look at what's in these metadata files. It has information about the partitioning, it has information about the schema, and it also has information about your snapshots, like how often you are writing, how much amount of data is there. And you can really imagine that, for really large tables, these files can run into hundreds of megabytes or even gigabytes of data with thousands of entries. So you could really query it directly, but it's not human readable. And that's exactly where the assistant adds value by abstracting this complexity away. These files go super long. And even if we kind of try to simplify this and go to the initial method that we've been using of querying our tables using SQL, it's going to still take time and expertise. So here on the left, you can see a naive data query. It scans terabytes and costs dollars per run. And on the right is a smart metadata query that you can use to query like the metadata, but it's going to only scan kilobytes, executes in milliseconds, and gives you similar insights from metadata alone. But to get there, you kind of still need to know what to ask for. And this is why we layered an LLM on top of this metadata. So instead of writing even the right SQL, you can just ask questions naturally. And here's a quick look at what's really been happening under the hood. So the metadata files are chunked and they're stored as embeddings in a vector database. In my case, I use Chroma. When you ask a question, the system will run a semantic search to pull the most relevant piece of metadata, send that context to the LLM, and then generate an answer. So it's basically a retrieval augmented generation or a RAG pipeline, but purpose-built for the metadata layer. So every insight you get is actually grounded in your actual data, and it's enriched with reasoning from the model, which makes the output not just accurate, but pretty intelligent. This is just an example of the tool. We saw that multi-turn conversations are possible. Doing the same thing in SQL is non-trivial, and we won't probably get the same richness of detail and reasoning capabilities. So I think here's the real power of this tool. It can really be customized. Like you can control the behavior via prompting. You can define adaptive reasoning levels. You can customize the input. So maybe there's only certain tables that you want to put through this tool to derive insights. So you can kind of control what kind of things you want to get insights on. This is also productionizable. So and you can add guardrails to control data modifications and also ensure that access rules are met. So I think there's a lot of power and potential of this tool. So kind of stepping back, summarizing, what we've really built is a new kind of data intelligence layer. it brings in natural language understanding, so you can simply ask data your data questions. So to handle all the potential breaking changes, give you recommendations. So, in short, it turns metadata into an active intelligence system, and not something you just query, but something that actively helps you manage and improve your data. So in a way, it's not just descriptive, it's also prescriptive, as I like to call it. So I think the future belongs to data lakehouses that kind of understand their own data, optimize themselves, and provide intelligent insights without human intervention. So this is where it all gets really exciting. We're moving towards self-aware systems, data that knows itself, it's self-optimizing, and of course, self-healing. So that's the vision, where AI doesn't just help us analyze data, it helps manage the data itself. Thank you. So that's about what I had for my talk. In summary, metadata is a very powerful source of information. It saves us a lot of query time while enabling agents to easily function at the metadata layer of the stack. So the future isn't just AI that understands the data, it's the data that understands itself and tells you what all you can unleash with it. So I think it's a whole new level of potential that's just waiting to be unlocked. And with that, I think I can open up for questions.
Yes, thank you, Srishti. That was very, very insightful to see data taking care of itself using LLMs. Very cool. So yeah, so we have a couple of questions in the Q&A.
All right. Yeah, I see the first question about, can we get something like, what are the top 5 tables with the highest daily usage? Yeah, of course. I think you can, it depends on what information you have in your metadata. So maybe if there's a lot of commits that's happening to your data, you could figure out and get information about what's the highest usage. Or I think there's also ways in which you can extend this tool. So I think you can also take in probably some other ways in which your enterprise is tracking the usage of these tables, kind of hook it up in the same system so that you can also make these kind of questions even more broader to get more insights. So, okay, there's one more question. So you said that you could create a vector DB with the metadata information. Do you refresh the DB when the snapshot lands or when new partitions get created? Awesome. So yeah, that's a pretty good question. So at least in the Iceberg world, metadata is dynamic. It's constantly evolving. Whenever there's any change that's made or there's a new commit, which goes under the snapshots, like we looked at in the metadata file, there's a new metadata.json file. So currently, I did it in a static manner. So whenever there was a new metadata file, I would just re-embed the diff between the two metadata files, which just kind of use a JSON diff checker to figure out what's the diff between my current and my previous metadata. And I would only put that into the vector, to my vector store, so that to minimize the kind of compute that's involved in this whole process. So yeah, I think right now it's in a more static way to just re-embed the diff of the metadata JSONs into the vector store to derive insights from it. But I'm sure the solution can be extended to make it more dynamic and do it on the fly. So okay, there's another question. How do you compose your metadata file? And how did you make it available to the LLM your AI assistant is using? So yeah, of course. So my metadata file is not something that I made. These are files that, so in the data lakehouse architecture, as we saw, there's a storage layer, there's a catalog layer, and then there's the access layer on the top. So the metadata is essentially managing or has information about all the data that you have in your tables. And one of the ways of managing this is through an open table format like Apache Iceberg, which has probably become the most popular in today's time. So Apache Iceberg, these Iceberg tables maintain their own metadata files. So every time, so they are the ones who actually have this information. So at the time when you create this Iceberg table, Iceberg itself takes care of populating these metadata files, and you can go and find this file in your object storage. So every time you make a new commit or you write more data into your into your data lake, a new file is created for every new commit, and you can find that information in your data lake. So this is just how Iceberg is generating these files. So I took these files, and in order to make them available to the LLM, I basically took all the files that was there in all the metadata files that were there pertaining to the tables in my data lake, and I did some sort of chunking in them so that semantically you're only clubbing certain things, and then creating vector embeddings for those, and then storing them in the vector store and using LLM to kind of query it and get insights from it. So I hope that makes sense. And yeah, I think there's one more question that I see. What tools do you use or recommend for capturing data updates? So I think in my case, I have just used the metadata because it's the real source of truth. It has all the information about whatever changed, if there was a partition change, if there was a schema change, if anything new was written, what kind of operations happened, whether it was a append operation where you're just writing more data. There's also a rewrite operation where you're taking some of the files and rewriting it through that process known as compaction that I had mentioned. So I think right now for capturing data updates, I have been just referring to the metadata and how often it's getting updated. But I think you can obviously probably hook up some sort of an architecture, like an event-driven architecture. I would probably just listen on all the updates or every time a new metadata is written in your object store and kind of just notify you. So you can obviously hook up an event-driven architecture to listen to these updates and notify you. So it all depends on the use case that you want to build it for. Okay, I think I see one more question. Do you have any GitHub repo or post with more details? Yes, I do have a GitHub repo. It is not, it's not public yet, but I do intend to do it. So I can probably do it and share the details through the Wova apps that's being used for this talk.